Hello everybody. Today I will be talking about some, let's call them preliminary strides towards the efficient and automated side channel evaluations at design time. So first of all, when I say design time, I'm specifically targeting standard cell, ASIC, hardware, digital design for hardware. So because I don't know if you, or not all of you work on that, just a few basic preliminaries. So if you want to design a digital chip, you sort of want to break it into a bunch of abstraction levels. So it starts with an idea, you write your VHDL, or in this case variable code, and you call this behavioral stage because you're sort of describing behavior in one of your preferred HDLs. Then what happens is you use these magical tools and you synthesize this code and you translate it into these things called logic cells or standard cells. In this case we have two, where there's like one AND gate and one D flip-flop. And this is usually called the structural level. In this particular talk we will be differentiating between a SYN, which is like synthesized, and GLN, which is gate level netlist. The only difference is basically whether you synthesize your design to just a generic and D flip-flop, or you're targeting a particular one with a particular drive, etc. from a library. Then what happens, you actually, because in the end you want to make a physical chip, next step in your output is basically something like this. There's actual layout with all these layers on the chip, but since you would have to work with SPICE or you have to work with analog simulations at this point, there's been decades of work in the EDA industry to sort of take these little interconnections and the effects of layout and model them as these sort of resistors and capacitors. This isn't working. Anyway, so this is called the physical level, and sorry, I have some pop-ups in Chinese. I have no idea what it's, but anyway, in the end you get the chip, right? So this is how the whole design process is broken into parts. Other way of looking at it is sort of to put all of this in a flow, and these are just the steps I just described. So you logic synthesis, you translate to a library, and you get to the physical thing. In the end, normally what you do, you manufacture a chip and then you start doing measurements. These measurements are basically just to verify that you're in the power budget, that the chip is a function and all that. But during the design itself, between all of these stages, you keep asking yourself a question like, does this, again, meet the timing? Is it big enough, small enough? Does it meet the power and energy constraints? So this is something that has been done for decades already, right? So what about such evaluations? They're fairly new, and for the most part, in the beginning, right, you would just manufacture a chip, and then you start doing these measurements. But this is, of course, a very costly process, because if you have a mistake there, you would have to go back to the very beginning, and it isn't very practical. So once a designer wants to make a side channel secure device, what sort of evaluations that are done in design time, mostly in like 90% of the cases, what happens is people are doing this sort of FPGA prototyping. So you take your behavioral code, you map it onto FPGA, and then you measure this FPGA. And while this works, especially if you look at designs like these, all these masking approaches where they're basically making very minimum assumptions on hardware, this seems to work, but does it really? We don't know, because there can never be a one-to-one mapping because of the different structure of the FPGA and the chip we're trying to make. What's sort of a fad nowadays is something that's also been done in the digital industry for a while now, is you do a formal verification. Whether this hazard algebra works by Bertoni, Martinoli, or the newest advancements in Eurocrypt. So again, basically we'll take this behavioral code or the netlist, and you are going to do some sort of formal verification on it. So this is not what we'll be talking about. What we're talking about is using these sort of simulation-based evaluations. And within them, again, already what's in there in the EDA world is that basically you have all these little design stages and these questions that you keep asking between them. So what we want to propose is basically just using the same approach, just in addition to asking this question, ask a question of SEA security, in more detail, what we're going to be doing is mostly leakage detection using a popular method. One thing to point out here, this has been done already. So people have been using simulations, especially when designing secure logic styles, for instance. But in most of the works, or all of the works that we've read, like, there are no details about this. There are no details about performance. People just do it and say, yeah, sure, this leaks or it doesn't leak. So this is basically what we'll be focusing on. So these simulation-based evaluations. So again, the goals of this talk is simulation-based evaluations. So first of all, it's not a replacement for post-silicon evaluations, and it's not a replacement for any of the other methodologies. So whatever you want to use, you can use. This is just like another tool in the designer's toolbox. What it is meant to achieve is to first decrease the effort of the designers, eventually shorten time to market of the devices, and sort of increase the confidence in the design that you're manufacturing prior to manufacturing. So get something that's more reliably secure. Why simulations? So first of all, by doing this, we're sort of working with a one-to-one model of the ASIC chip we're trying to manufacture. So we're not hindered by any differences that FPGA introduces or faults of your mathematical model if you're doing formal verification, but we're focusing the X chip. Second of all, since it's a design time method, we can easily, again, without anything else, we can just say, okay, we're just focusing on one critical thing, like an S-box, and just forget about everything else. They're inherently parallel to compute, because if you want to just keep collecting traces, right, like you would do in measurements, well, here you just sort of say, okay, I take 10,000 here and 10,000 here, and everything works perfectly, so they're relatively efficient to compute. And again, what cannot be achieved through other methods is you get this noiseless, high precision observations. You get like a floating point precision, which is allowing us to have basically unrealistically clear view of the device, and gives a potential to view, to get and then see the smallest of the insecurity, so to speak. But then there are also the cons. So first of all, they're as accurate as the models they're using. These models usually cannot capture the artifacts of manufacturing, and they are limited in a way. And second of all, again, these noiseless high precision observations, they're a strength but they're also a weakness, because we might be protecting against something that just cannot be seen in real life. Looking at it, this use of simulations in this sort of leakage detection, let's say, or design time evaluations, we think that there is like a couple of practical requirements that need to be fulfilled. So first of all, they have to be available early in the design flow. So you can pretty much, like for the timing closer, so you can start working with this and you can start detecting flaws very early. Second of all, it should be fast, because I mean, if it takes 2 months to evaluate, yeah, you're losing time anyway, and it should be scalable in terms of circuit sizes. Lastly, it really needs to have like a high confidence. In order for it to be applicable in practice, it should provide like a high confidence in the security of the manufactured devices. In this talk, we'll be focusing on the first two, because pretty much the third one requires you to take a chip and do measurements, and that's something that's under construction. But there's also one more requirement. If we really want this to be practical, we have to make it compatible with the commercial EDA tools. I've said it again, already, and I'll say it again. Like, there's like tremendous knowledge base, decades of work, very smart people. So this is something that we will want to build upon. So as you've seen so far, like there's many abstraction levels, many models, many things. So we sort of wanted to find a way to put it all together. This resulted in a framework which can otherwise be called Computer-Aided Side Channel Analysis Design Environment, or very conveniently called CASCADE. This is the overview of the entire framework, which is supposed to provide sort of a full stack support for the ASIC development. There's a lot on the picture, and if you want to get into the details, you can read the paper, you can contact me. What's important here to see is that there are basically 5 important parts of it. So first of all, just usability-wise, this is Session Manager, which is sort of the central part, which is managing all the parameters, and this is the guy you talk to basically all the time. And then when you talk to this guy, it will allow you, or girl, it will allow you access to basically handlers, analyzers, parsers, and generators, being the 4 main components. And the way you would typically use it, I'm going to say something about each of these in particular. So basically you start with a session manager and you have your idea, you have your configuration, your design, you put it in there, and then this blob will basically represent like these sort of system stored configured data or parameters. So then what you want to do is at any moment you can independently access any of the components, and now you as the designer, you first usually want to go to use one of the generators and generate something like a test bench, or it's usually something that aids automation, test bench, test vector, or something like that. Then where you go to handlers. Handlers basically encapsulate EDA tools, encapsulate some custom tools, but the idea of it is to sort of abstract away the functionality. So whether you want to use, I don't know, a Synopsys design compiler or whatever cadence is equivalent of that is, you can have this sort of encapsulated way of handling it and hiding it away from the designers. So here you're using this sort of system sort parameters, and then once you're doing the synthesis, this little bluish circle is basically where you have the only interaction, because like additional user manual input, because yeah, automating the synthesis, be it the physical, the logical synthesis, that's a whole other problem. So you would synthesize and you would create something like a new stage. So this is like a gate level netlist or power netlist or whatever, right? So then you would also want to simulate them using one of the simulators from the framework. And these simulators would again rely on these automatically generated data and the typical netlist that you start on to generate an output. So once you have this output of a simulator, you will start parsing it using one of our parsers, which are written in C, optimize, etc. At this point, we just want to say, so no matter the input, whether it's spice or it's just logical simulation, this double counting, we sort of store it in a custom binary. This custom binary essentially, I mean, it has a lot of things around, but at its core, it's basically, it allows you to efficiently extract data from netlist and store it like in the input-output and sort of target for the analysis. The data values followed by the samples of your simulated trace. Bohan, you have to do a COSIC weekly in 5 minutes. Anyway, once you have this file, at this moment you can handle it pretty much uniformly, no matter where it came from, and then you can start playing around with the analyzers. Analyzers are working with these files, and they can include any sort of evaluation method that you have out there in the wild. What we'll be showing in this work is basically we mostly rely on TVLA. It can be computed on the fly, it's pretty generic, you can apply it whether it's a small S-box or a whole design, and you're basically just trying to detect leakage. And again, we have other methods implemented, and whatever you want to add, it can be easily added to the framework. So this is sort of the roadmap of how to use each of the blocks. I've more or less said all of this. So yeah, parsers and analyzers. So this is basically Python, and this is implemented in C with very low level optimizations, and it's pretty fast. We will be focusing on TVLA analysis and that. So in terms of experiments, just to take a very small motivating example. So this is the DOM in-depth multiplier, basically an AND gate. Which is first order is SC secure under 2 assumptions. First one being independent inputs, and second one that this bit here is basically uniform and triangle. So what we do, we synthesize this circuit, we go through the whole motion, and we see that basically when we start at the very beginning, and so if everything is implemented and done correctly, everything is secure, and this basically differential trace or the TVLA trace is just a flat line. But then what happens is if you break one of these independence assumptions and you run this sort of TVLA, and no matter how simple the model, so this can be just based on a logical simulation, and delays can be constructed by just simple delta delay module. It says, okay, each gate in the cell has the same delay. You will start seeing some leakage. If you take the same circuit and you say, okay, we're going to turn off the mask, and you do the same thing, you will see the leakage again. But what's also interesting here, and what was like a driving thing for us, is that with this precision, you can not only know that there is leakage, but that maybe down the road you can, based on the position where the leakage occurs, you can actually talk about the source of it. So what kind of error there is. So this is a motivating example. We've tested our framework on a couple of other circuits, which include here. One of them is the threshold implementation of a present S-box, which is again, it's about 350 gate equivalent, so it's a bit bigger, but it's still a very small circuit. But since it has 3 shares and a total of 12 inputs, so basically the total number of traces that you can collect is equal to the number of possible transitions, which in non-trivial cases is around 16 million. Everything that we found for the small motivating circuit, everything, like all the findings hold. So if everything is running correctly, you have a flat line. Once you start introducing some sort of errors, such as just turning one of the shares off, you will see in the first order TVLA massive leakage. One other thing that we've seen is that if you're using, again, even these simple toggle counting, let's say, models, which can be used in the very early design stages. So basically the delta delay, as soon as you have a netlist, or just zero delay or delta delay that is some value, you can start detecting leakage and you will get it. So this is just the evolution of the trace. So with the increasing number of, so you basically plot the absolute of the maximum of these traces with the increasing number of frames, and you'll see that even using these very simple models in the beginning, you can start detecting leakage. Okay, they're not as good, so maybe you should just go and synthesize your design, but anyway, even the simple models can detect leakage. We repeated these experiments with more complex Liberty models and using more complex simulators. Everything holds, but again, as a simple case, we showcase this. Now, one other thing, since so far we've talked about this masking thing, and we've said, okay, masking is very popular because it can be formalized, but also there are these, for instance, WDL implementations of the entire S layer of present. So WDL is it's a secure logic style based on differential logic. It can be implemented using standard cells, which is so basically this approach can be applied to any sort of digital design that's based on standard cells. This is just the principle. So basically, if you want to have one wire, you would have a wire and its complement, and then you have to store them differently. And the idea is that you have, like, if you have an AND gate, you have a complementary OR gate, and no matter what the transition, no matter what the input, you will have the same number of toggles in the circuit. And this is how WDL wants to make the power consumption independent in the circuit. Applying it to this, basically the S layer of the present block cipher, we try to detect leakage. So now this is up to 10 million traces. We did not detect any leakage that is, I think, dangerous, or like we're still within the confidence interval of the t-test. But what's interesting to see is that, or what's interesting to say here is first that once you have a GLN, which is using this just a synthesized netlist with some statistically extracted delays of wires, you have significantly less leakage. But if you actually place in Rado design and you get all the asymmetries, the leakage is getting considerably higher. Now, this could have been ran for long, but one of the points here is that this is again a design methodology which should provide a certain confidence. We cannot say that in the end this will be secure because this isn't leaking, because we know that as you start manufacturing with process variations and things that can increase this leaking, that can decrease the security. But also on the other hand, if you get something that's secure up to 10 million traces, well, this usually exceeds the lifetime of a device. So again, it can be applicable, and what we wanted to show is efficient and it can be done early, and we show the findings there. So first of all, there was a big questions about all these. How does it scale? Because for instance, if you take SPICE and I mean it's the best analog model, etc., but you have this exponential increase in processing times with the increase of the gate sizes. So if you're using these sort of logic simulators and also the more sophisticated power simulators that are on gate level as well, they scale pretty much the same. But the idea is that here we plot different designs, and we sort of take the placed and routed designs with all the parasitics, so it's basically as complicated as it gets. And we say how much time do we need to sort of simulate and process 1 million traces on a single thread of this particular desktop workstation. And moreover, for the processing, we say, okay, we do second order TVLA just to be, let's see. So first order TVLA is even faster. So the parsing and this and the TVLA, and we see that basically, well, for smaller circuits. So this is basically this here is 10 kilogate equivalent. So the majority of the building blocks, or the majority of designs you'll start working on, I mean, it's really a matter of minutes, and the time required to simulate and process is pretty it's comparable. As you increase, and then we just for the scalability, we said, okay, we're just going to take the full unrolled AES, no security there, but I mean, simulation tools don't care about security, which is about 127,000 gate equivalents. We see that although there is an increase in the simulation time, it is still manageable. So in total, this would be around 32 hours. Again, you parallelize it on the 8 cores of this thing, and you have this million in 4 hours. So in this sense, we believe this is indeed can provide these very fast early estimates and is scalable. So in the end, if you start scaling up, the performance of our tools is just becoming negligible compared to the performance of the commercial EDA tools. So in terms of utility, what we see is that, as you said, we based it all on commercial tools and all the simulators. We don't want to reinvent the wheel, but we built it on that, and we sort of built extensions to it, so it can be easily adapted into designer's toolbox, and it can easily be extended if you want to use a new simulator or a new model or something like that. I've already mentioned this, so very efficient preliminary estimates. And then this is something that we'll be using it also. So other than just using it to sort of detect leakage in designs, we're going to use it for a basis to study further models and metrics and see how this can be improved. Also, the community will be able to access it at this link. I'm still putting all these things up there. It's not all there, but yeah, be patient, and then it will be there. Also, if anybody wants to contact me, we can discuss this. So for future, as I said, there's this point number 3, which is comparison against an actual ASIC chip. We have one, courtesy of ETH Zurich and Nene here. So we can actually see what of these parameters needs to be taken into account, how to calibrate models, etc. Increasing the model parameters, again related to the starting from here. And then we will also plan to look at how these sort of the back-end part of the whole problem. So yeah, thank you.
Questions for Danilo?
Yep. Question. So feedback, I think this is slide 13 that you either way went through it very fast, as well as the one before. I mean, I don't know how you did on time, I'm assuming.
24, I mean, so the sessions are half an hour,
yeah,
so
you did good. So I think it would be more interesting rather than this slide and the previous one even, maybe?
Okay.
Because the previous one, you can already tell more or less the blocks in the one before, but I think it would be nice if you show a couple of traces with different models.
Okay.
Because the first time that you talk about models, that you say delta 0 larger than 0, this comes a little out of nowhere. So now seeing all the flow, I think it's nice that you don't need to go into the details, but to show you have the figure in the
Yeah,
paper,
the
the one with impulses and rectangles, triangles, whatever the different, or even the spice if you want to add. I think that's nice to see.
Either here or earlier where you explained the different levels of abstraction, that you say, I mean, who will be there listening to your talk? Right? So if these are people who have never done chip design, then you show how a typical simulation looks like at the RTL level. I mean, more staircase things. So, but when you go to SPICE, it's really analog waves and things like that. So you can do it here or you can do it later. And then you say, okay, already at the highest level of your sticks, I have already input, right? And then you can say, weighted sticks, the basics. Otherwise, you're going to lose maybe more. And just practical, the black letters on the brownish background are very difficult to read.
Okay. But it's
Go further when it's only a picture. Like, this. Next. Here, like the back dot EFF and EFF and dot AFD. They're inside a brown box. They're very difficult to read.
And then in synthesize, you said the blue circle.
Yeah, I didn't see blue circle.
Did we? I don't know if it
yeah,
was
this is, yeah, it's
because
light
it's
bluish
bluish
anyway.
a little from here. But make it, if you give the slide maybe stronger.
Okay.
I think the slide that you can make a point is the one that you have the different models actually.
Okay.
Which one? I don't know what it is. You have the right number for that. I don't know, 15, 16?
No.
More. You know, this one.
This?
Because then, basically what you can stress here is that, of course, the more accurate your model is, if there is leakage, you will capture it earlier. But then at some point, there's the line with reality, yeah? Like, maybe at some point, if you keep going, SPICE will give you, you know, that you can break anything, and in reality, you cannot. So somewhere, you can use this plot to argue about this gap between real chip and what the most accurate simulations will give you. Because in WDL it almost go that direction, so maybe there is a good place to say it.
Yep.
Is it WDL example? And also, so this present, is it again the split up present S-box?
No,
Or
no,
the
no.
S layer is completely in one cycle?
It's one cycle parallel S layer.
Okay.
So-
Out of curiosity, it's interesting to see such a picture for AES also, which is
No, it's
for WDL and AES combination, because present S-box has lower end depth and lower
Okay.
depth in general, right?
yeah.
And my understanding is that WDL becomes more and more vulnerable to timing problems as the depth increases. It's my understanding. So I was wondering how much we would see here. It's just out of curiosity.
No, so the way I
What's often called early propagation
Yeah.
or early termination.
Well, as your design becomes deeper,
Yes.
the timing differences have the potential to become larger. Yes.
Yes. Yes. So I was just curious how would the analysis be on an AES systems? Something with a different depth.
we can run it, but what I was going for here is that basically, so here you just use the power of the GLN, because if you use these simpler models, everything is symmetrical, right? Because you have all the gates, and if you just get a flat line, and I mean, drawing a flat line is not that exciting. I would expect the exact same behavior. Maybe AES would because it's bigger, all the asymmetries. So yeah, also this is why we took the whole S layer, so 16 or how many is there? Because if you have one, then you have smaller differences, and you have like everything is way more symmetrical, right? Whereas if you have a bigger stack, if you have them all, then you will have, depending on the position of the wiring and all that, you will have more asymmetries, and then this will become more prominent. So, but again, this is like no special routing. This is just press a button and it routes it.
So this is random routing.
This is random routing, yeah.
So it should leak at some point.
It should leak at some point, yes.
This is why
But if it doesn't leak,
it needs to leak.
if it doesn't leak within cases, it's noise free. Yeah, this is noise free, right?
This was
This mustn't be something.
Yeah, so
I know, but it doesn't take the route. Does you take the routing into account?
yeah. I
Routing
mean,
imbalances?
so in the orange trace I do. Here there is no writing. Here you just put some statistical whatever thingies. But
this is also what the tools report.
yeah, this is what the tools report. Yeah.
I mean the EDA tools.
But then why doesn't it catch it? Do you have only the S layer, or it has inputs and outputs? Does it have output loads? Does it drive anything?
It has.
You have only the little wires inside of the S box, then that's maybe the explanation.
It drives. I mean, it has the load equivalent to the like input pin of our register. So.
This box is really small, right? I mean,
Maybe that's why.
it's just possible that the difference is tiny. And then
But it's noise free. It should jump on anything.
No, it depends on your extract model. Eh? How does parasitic extraction work? Parasitic extraction, I mean, can give you very precise coupling between neighbors, but if the parasitic SL is very rough, I don't know which tool you use. It just gives you capacitance to ground, and that's it, right? But that's out of his control. That's the tool. But, that's what these tools are. EDA tools are.
Yeah, but it's important to understand
How it behaves.
the limitations, or I mean, how much do I rely on the accuracy of the tools?
Yeah.
So there's two reasons why it should leak at some point.
I mean,
make a difference if the EDA tools were forced for area optimization, let's say, and then compressed so that the wires.
I don't think for area.
Or for another metric, I don't know.
Because if you optimize for area, the wires are short and
Yes,
capacitors.
or maybe the other way around.
Optimize for large area, we don't do that, right?
No, not like
Oh, we do.
push the frequency. I don't know.
Right, if you push for frequency, then you have short critical path that goes against your,
That's also.
you want the long critical path.
Yeah.
It's also the quality of the standard cell library. Hopefully in a school exor cells, then it's also much better than having it composes in end and orbits. Right? So that's the library cells. Cool. Nice.
Good. Thanks again.